Alright, as you know, there are random errors and there are systematic errors. So what's the difference? As usual, let me use an example. So suppose you are doing an experiment. So you are dropping a ball at a certain height h, and then you are going to use a stopwatch to time how long it takes for the ball to reach the ground. What do we do with the data? Yeah. So we know that the height is related to the time by the equation h is equals to half gt square. So by plotting h against t square, we expect to get a straight line graph that passes through the origin with a gradients that correspond to half g. So using your data, you plot the first one, you plot the second one, you plot the third data point, fourth data point, fifth data point, sixth data point. Wow, they line up perfectly in a straight line. So you quickly draw the best fit line. Oh, it indeed passes through the origin. So quickly calculate the gradients of the best fit line, equate it to half g, and you calculate g to be 9.81 meter per second square. Your teacher calls you a genius. That's when you wake up from your dream. Yep, your graph is showing that your data has no errors at all. No, that's not possible in real life. So in real life, you are more likely to get a graph that looks like this. Yeah. So how would you describe your data points? So they are scattered randomly about your best fit line. Yeah, scattered randomly. So what could be the cause of this scatter? A simple reason could simply be the resolution of your ruler. Yeah. So maybe the actual value is 1.29 cm maybe, but your ruler has a resolution of 0.1 mm, 1 mm, right? So you are going to record it as 1.3 cm. So that will cause your h values to be larger than the actual. And of course, at times when the actual value is like 1.31 cm, because of the resolution of your ruler, you are going to end up recording it as 1.3 cm. So on these occasions, your values of h will be smaller than the actual ones. This is not the only possible cause of random error. Maybe it's parallax also. So maybe you're not careful. Sometimes you position your eye above the line. Sometimes you position it below. So this will cause your values of h to fluctuate above and below the actual values as well. Or it could be simply you're clumsy, right? Sometimes you position the ball slightly below. Sometimes you position it slightly above the intended position. So that will also cause random fluctuations. So the keyword is random. Because it's random, it can be, the error can be of different magnitude in either direction. But exactly because it's random, when you draw the best fit line, you kind of get the random errors to cancel one another out. Yeah. And another thing you should do is, of course, to repeat an average. So for example, you shouldn't just drop the ball one time. Yeah? You should repeat and take the data again, and maybe again, and then take the average. So if you do that, you're more likely to reduce the random errors, and then maybe you have a chance to get a graph that looks more like that. Okay? So do you notice that actually random errors doesn't cause any inaccuracy, because the gradient of your best fit line actually is not affected. So you are still going to get a very accurate value for G. Not so if your errors are systematic. Yeah? So if you get a graph like this, it's very clear that you have a systematic error, because it looks like your values of h are always too large, and it's always too large by the same amount. So what could be the cause for such a systematic error? Well, if you are using a vernier calipers or micrometer screw gauge, the usual culprit is a zero error. But if you are using a meter rule, does a meter rule have a zero error? Maybe, yeah. You know, some rulers, the zero mark is not at the edge of the ruler. So some students are not aware of this. Then they'll get a random error. Or some rulers are so worn out that the front part of the ruler has been chipped away. The edge of the ruler is actually not the zero mark. so that you can also get a zero error that way. But actually there's a more interesting way to get such an error. There will be students who measure the wrong age. They measure it from the top of the ball instead of from the bottom of the ball. So that will definitely cause your values of age to be consistently larger and by the same amount. But this error is still not so bad, you know. You see, it actually doesn't affect the gradient of your best fit line. So you are still going to get the correct value of G. It's just that it's going to be a bit embarrassing because everybody will look at your graph and know that there was a systematic error in your experiment. I think a worse graph to get would be something that looks like this. What kind of error are we looking at? So it looks like your value of age are all too large, and they are too large by a fixed proportion, and that's why your data points still line up straight, but it has a gradient that's too steep. So what could be a cause for such a systematic error? Well, maybe your ruler is crap, yeah? Maybe on your ruler, every cm on your ruler is shorter than what 1 cm is supposed to be. But that's not very likely. I think a more likely cause of this error is the student did not align the ruler straight. Maybe the student aligned the ruler at an angle theta to the vertical. So because of that, instead of measuring this value h, the student end up measuring this value. I'm going to call this big H, yeah? So small h is actually big H cosine theta, which means the value of h that you measured is always larger than the actual value by a constant factor of 1 divided by cosine theta. So that will explain the graph that you get here. So this is a bad error because the gradient of your line is actually now too large. Yeah? So this will cause you to get an incorrect value for the value of G. But this is still not the worst graph to get, you know. I think the worst graph is something that looks like this. It's not even a straight line. You can't even draw a best fit straight line. You got a very obvious curve trend, and you need a best fit curve. So what could be the cause for such a thing? Well, maybe the error is in your timing. Maybe all your timings are too short, yeah? Maybe the lag, your human reaction time, when you start the stopwatch, is always larger than your human reaction time when you stop the stopwatch. This can happen if you are maybe you are doing pair work, and then your buddy is the one who is releasing the ball and you are the one operating the stopwatch, and your friend doesn't give you any warning when he releases the ball. So in such a case, your timing are all going to be too short. Then you're going to ask, then why doesn't it cause the graph to just shift leftward, right? It will still be a straight line. Well, it's because we are plotting t squared. We are not plotting t. Because we are plotting t squared, a consistent error in t will cause your graph to shift by a different amount, and because of that you end up with a curved graph. Okay, so I've shown you different ways random and systematic errors can cause trouble to your graph. So the main idea is random errors are random. So because they are random, they are actually quite easy to manage. You can just repeat an average and the random errors will cancel one another out. Random errors actually is not a big problem. It actually shouldn't lead to inaccuracy. It only leads to poor precision. Yeah, but systematic errors, that's the one. Most of the time, systematic errors will cause inaccuracy because you cannot just eliminate them by repeating and averaging. So what you have to do is to identify the source of error and then remove it and then correct all your data. Okay, that's all. Ta-ta!